So can I start?
Yes, yes, you're very welcome.
Начну я по-русски. The title of my talk is Finite and Homogeneous Particle System with Exclusion Interaction. Mikhail Menshikov, Department of Mathematical Science, Durham University. Вот. Но я хочу сказать, что эта работа очень семейная. В ней, значит, соавторы, значит, отец – это я, Михаил Васильевич Меньшиков. Дедушка – это Вадим Александрович Малышев. И два ребенка – Сережа Попов и Андрей Вейт. То есть это мои ученики. То есть вот такая вот длинная история. И так получилось, что эту работу мы начали при жизни Вадима Александровича, закончили фактически при его жизни, но но эта работа еще не опубликована. То есть она выйдет после смерти Вадима Александровича. Поэтому это вот такой вот исторический интересный факт. Ну а сейчас я начну тогда с работы. Значит, the exclusion process was started by maybe with Spitzer 1970 is a typical model of non-equilibrium statistical mechanics, representing the dynamics of a lattice gas with hard-core interaction between particles. We can see the system of n+1 in this now for sure finite particles on the one-dimensional integer lattice Z, performing continuous time nearest neighbor random walks with exclusion interaction in which each particle processes arbitrary finite positive jumps rates. The parameters are the left and right jumps rates associated to each particle. So for first particle, it will be A1, B1, for AI, BI for some ice particle, and AN+1, BN+1 for the last one. So A1 will be the rate for particle I to try to jump to the left, and BI will be the rate of jumping to the right. The inclusion constraint means that there can be at most one particle at any site of Z at any given time. So attempt jumps are suppressed if the destination site is occupied already. Now, this page will be very important to understand because it will be what I'm going to say. It will be very simple, and this problem can be formulated for students of third year and understand the problem for sure. And so I like such problem which can be formulated for not for very deep specialists. So formally, a time homogeneous continuous time Markov chain is on xn+1, which is x1, x2, xn+1, which belongs to Zn. And x1 less than x2, and so on, less than xn+1. So what is x1? It is position of first particle on Z. xi will be position of ice particle on Z, and xn+1, the last one. So configuration x of t is vector x1 of t, xn+1 of t, which belongs to xn+1, so which is in Zn at time t. So in addition to position of n particles, we want to consider number of empty sites between particles I and I+1 at time t. And nu I of t is distance between position of I+1 particle and I particle. So it will be nu I of t is xi plus 1 of t minus xi of t minus 1. No, for I, which is 1 to n. So this is important picture. So in this picture, I have exactly 6 particles. 1, 2, 3, 4, 5, 6. So distance between, this is x1 of t is position of first particle, this is position of second, and I see the distance between first and second particle is 2. So there is one empty place between them. Between second and third, there are no empty space and distance is 1. Between second and third distance is 4 and there are 3 empty places. Here, fourth, fifth, and sixth particles are neighbors, and so there are no places between fourth and fifth and sixth place. So if at moment t I have such configuration, then first particle has possibilities to jump to the left and possibilities to jump to the right. And rates, we know it will be A1 and B1. Second particle has possibilities on jump to the left. And A2 is rate of this possible jump. This particle can't jump to the right because this place, the place where it wants to jump is already occupied by third particle. No, similar, so the particle number 5 will stay. There is no possibility to jump to the left and to the right. So here and for the moment we have possibility, we have A1, B1, A2, B3, and so on. It's clear what particle can do. The process nu of t, where nu of t is nu1 of t, nu n of t, so the number of empty places between corresponding particles, is also a continuous time Markov chain, which can be represented via Jackson network of n Qs MM1 type. I'll explain this later. The process nu can also be interpreted as a generalization with site-dependent rates and immigration at the boundaries of the zero range process on the finite set N. When I start this problem with Vadim Alexandrovich, I heard about zero range process, but I didn't know much about this. So I started this problem like continuous time Markov chain in some sense, but I'll tell about this a little later. Yet another interpretation of nu is as a random walk on the octant Zn with boundary reflection. Generically, the stability for such work is solvable only for n equal 1 or 2. So very old results of Kingman 61, MALYSHEV 70. But we show that our process admit a complete classification for every n. Okay, this moment I was going to go to Blackboard and explain everything, to do some dance and song about. So this moment I want to change a little bit to Russian. Maybe it will help me without Blackboard. Таким образом.
Sorry, there is also English-speaking participants. I just tell you.
Oh, okay. No, anyway, my English is because already 23 years I'm teaching English students, so it is with big Russian accent, but I can speak with the same speed like Russian, and I'll try to explain. So for n equals 1, it is not even. So we have only 2 particles, and distance between them is new, and we can write. So this will be, and this will be one-dimensional process, and we can simply find, because we have rates, we can find condition when this process is ergodic, when it will be transient, and in ergodic situation, it's possible to find special measure of this. When n equals 2, this will be so-called, which Albert Nikolaievich already said, it will be very famous results of Vadim Alexandrovich half century ago about random walk in a quadrant. And here you have inside it will be homogeneous random walk with jumps not more than square root of 2 and some boundary condition. And fortunately or unfortunately, in general case, we can't find special measure. We can find precise condition of ergodicity or transience, and this was also in probability language. It was paper of Vadim Alexandrovich in 72, and in 1970 this theorem was proved by analytic approach. But if you want to find special measure, it will be some automorphism Galois, Riemann surfaces, and so on. And in reality, it is impossible to find precise formula even for special measure. But our process with exclusion has rather general jumps inside quadrant, but specific reflection. And this specific reflection will help us to find special measure precisely. So, and what is even much more, we can do it for any n. I know very small number of models, rather generous models, in which you can find precise solution. And this will be one of them. So this is what is important. So I hope that my dance was a little bit, but without blackboard, because I was going to show what kind of reflection is here and so on, but people can find later this problem. In archive, it's possible to find this paper. Okay. Our main result is to characterize the long-term dynamics of the particle system and explicit stability classification and description of particle dynamics, law of large numbers and fluctuation. So in reality, what we have here is, so our main result exhibits a unique partition of the system determined by the parameters AI, BI into maximal stable subsystem, which we call stable clouds. So we have n particles. All of them have their rates, and they can't change their rates in future. And at the end, it will be some dynamics. So our main result will be, if I speak in normal language, it will be that at the end, our system will be divided by subsystems of particles, which we will call clouds. And any cloud will move with their own speed. So it will be some speed, some clouds. And inside cloud, it will be, all particles will be close to each other. And here we can find even special measure. So distance between particles, it's possible to find distribution of this. It is very strange. So it means that if you will give me, for example, 6 particles and give me rates, using only calculator, I can find speeds with which particles will go formally. And even if I'll tell you, for example, first and second particle will be subcloud, third will be single subcloud, fifth and sixth will be also some cloud. And we can find speeds, and also we'll find what, when t turns to infinity, what will be distribution of distance between these particles. For me, it was very exciting, and for Vadim Alexandrovich too. So we were possible to find such results. Also, later it is possible to do some machinery, and also we can the location of each stable clouds always a strong law of large numbers with an explicit speed. So speeds of clouds are non-decreasing left to right. So it will be the cloud partition is characterized by a finite not linear system, which is the translation of our setting of the classical Goodman and Massey equations for Jackson networks. So we have in Jackson machinery, we have Jackson, who was the first, and what is very important, Goodman and Massey. Because Jackson didn't know what to do if his queuing system is not stable. But Goodman and Massey was possible to find subqueues which will be stable and which will be not stable. Moreover, we show that the cloud partition can be obtained by a linear time algorithm of elementary steps, streaming an algorithm of Goodman and Massey from the Jackson context. So which numbers I must calculate if I have calculator? So what the result will be formulated through these numbers. So assume that AI is more or equal than 0, less than infinite. BI more than 0, less than infinite, for all I belongs to n plus 1. For discrete interval I, from L to L plus m minus 1, so this interval has m elements, define alpha of I, which is alpha from L and m. So this will be product of these fractions. Who know random environment, Sinai regime, random environment? It's also you need to study some their potentials, and so it will be some such products. So in reality, the answer will be connected with standard technique of random environment. And in reality, I am not going to speak today, but this is possible generalization, and it's possible also consider when you have not only finitely, but infinitely many particles, but in specific, and if you have, and you must study such products, and you can even find many. Now we are doing this problem, we are thinking about this problem and did already a lot with Andrew Wade and Sergei Popov, but unfortunately without Vadim Alexandrovich. But this is like what is possible to do. So we have such products, and also beta will be this. So to understand better what will happen if L equal 1, so alpha 1m, it will be product of all AIs, so AIs are raised to the left, divided by product of BIs jumps to the right. And beta, it will be such, no, it's listen only the talk, it's difficult to understand why this is important. But I want to demonstrate which numbers I need to know. Then we can define V with the head of I, which will be 1 minus alpha of I over beta of I. Finally, for m more equals than 2, define for G equal L to m minus 1, such value rho with head I of J. You see that it's again will be some formula with this alpha. So if I know AIs and BIs, all can be calculated. So recall V with head of I is 1 minus alpha of I over beta of I. So interpretation of V with tilde later will be, it is a putative speed for the particle cloud. So in reality, if our cloud, we will check, it is stable, it will be, this will be precisely the speed of this particle, this cloud, physically. So if you simulate this model, then you will see that everything will be divided by clouds. Every cloud has speed. We will have law of large numbers for them, and even center limit theorem it's possible to show. And this will be speeds of these clouds. Interpretation of, so if it is one-dimensional, so if you have only two particles, then speed will be, if you have only one particle, then speed will be BI minus AI. So BI is rate to go to the right, AI to the left. So the difference will be our speed of this particle. This is evident, and any student of third year who understand continuous time Markov chain, and this, it will be very clear. And who can't understand in future, he will not get satisfactory mark. But if you have already two particles, it is not so, it is already some interesting calculations for how to find what is speed and what is rho, and so on. Interpretation of rho is as a stability parameter is correspond in the language of queuing theory to a Vogt load. So who knows, who is interested in queuing, they know that Mr. Jackson used such load, and this is important. And this Vogt load for the queue associated with gap J in the subsystem I. So gap J, it is distance between particle J and J plus 1. So part of our results will be to identify an order partition theta 1, theta n of n plus 1, in which each theta is a stable cloud. So theta 1 will be first cloud, theta n small will be the last one in the long-term dynamics of the particle system. Given in order partition theta, write for theta plus, it is the number of theta j for where number of particles in J cloud is more or equal than 2 for the ordered non-singleton if theta j equal 1. So we will have clouds and also and single particles. So it's a little bit formal, because I prepared my talk. I don't like in such a way because maybe it's more, but I'll follow this. For I equal from L to M, a discrete interval with M more equals than 2 elements, write E alpha, E0, interval from L to M for the discrete subintervals that omits the maximal elements if I more equals than 2. Define new I of t, the set of all new j for j belongs to this I0. The vector of particle separations restricted to particle in I. Stability means that the relative displacement of the particles indexed by theta are ergodic. Limit distribution will be of the form product of this rho to power zi 1 minus p L of j. Okay, so I'll tell it in more simple way. So if we have a cloud, and we will know how to understand that this is a cloud, then using Massey system, we can find these rows. These rows will be some, and you saw that I was possible to find these rows. So if these rows will be less than 1, then we can limit distribution will be exponential, geometrical, like in Jackson network. So in this case, if we will try to solve VADIM Malyshev's problem in the quadrant, and if it will be our problem with reflection, which we can find for Jackson, and if we know that it will be ergodic, then distribution will be exponential and independent. So for sure, Vadim Alexandrovich didn't know about this 50 years ago and even 1 year ago. So what will happen? The stable cloud decomposition encoded in a general traffic equation of Goodman and Massey in the Jackson network setting. So this is not linear system. In Jackson, it was a linear system, but if we have, but when it is not ergodic, then we must solve not linear system. It's possible to do, no, not trivial. It's possible to solve this system with, but not with calculator. It's possible to do with good codes and computers. And I'm not going to do such problems at all in my future life. But we have some specific algorithm how to find these speeds and these rows, and then find special measures, even with calculator. But I am not sure that I prepared this algorithm with slides in future. I'll try to explain you, but unfortunately I don't have Blackboard. Okay, so what is vector mu? It's service rates and lambda arrival rates of exogenous customers, given by mu I equal bi plus alpha I plus 1. So in some sense, what it means? Distance between I and I plus 1, the number of empty spaces between I and I plus 1 particle, it will be our Q. And number of this will be the number of customers in ice queue. In this case, we have lambda 1. It is the rate with which particles come to first queue, but in our language it will be A1. It is rate of first particle jump to the left. Lambda n, it is the rate with which particles are coming to the last queue. Last queue, it is empty, it is space between the number of particles in this queue. It is distance between n and n plus 1 particle will be bn plus 1. All other lambdas are 0, so no particle will come to queues which are inside. And stochastic matrix in Jackson network, Pij, it will be with which customers, when they will be served in ice queue, with which they will jump to I-1 queue, will be Pi I-1, and we can calculate it through AIs and BIs, and Pi plus 1, it will be probability with which we. So here I construct, and this will be possible to explain, I construct one-to-one correspondence between our particle system inclusion with rates and some Jackson network. It is one-to-one correspondence. And now if we can get some results in Jackson network, we can interpret it for our particle system. But because our Jackson network is very specific, so you see that I have lambdas not 0 only for first and for last queue. Inside I have only the particles which will be served in middle queuing only can jump to another queues. They can't leave the system. We were possible to solve this equation in a more trivial way. So theory. MALYSHEV, Menshikov, Popov, Wade, 2022. So because this result last year. There exists a unique solution, nu I, to the general traffic equation. Defined rho i's, nu I over mu I, for every I belongs to n. Then there is a unique cloud partition theta of n plus 1, which we call the cloud partition such that for every theta belongs to theta with star, and all j belongs to theta 0, rho j equal rho with cloud, and rho maximum more or equal than 1 for every theta belongs to what I have defined with maximum theta less than n. So in reality, it will be possible to see maybe this later. So what we hold, if some rows are less than 1, then it means that load is less than 1, and this will correspond to distance between particles, which will have distribution, so it will be ergodic. And when rho will be more than, which is possible, will be more than 1, then for this situation, we don't have distance between particles will tend to infinity. What is important that equation of many good things about this partition. The problem is that to solve this non-linear system is not trivial, but we can demonstrate an algorithm which will be much better, and as I told, that if we will have only not many particles, I can give the answer even using only calculator. And maybe if spend long time even with pen and paper. But calculator, I am already motivated enough to use at least calculator. Okay, so also what we will have that our numbers nu I, which we will possible to calculate, this will be really our speed. So xi of t over t will be exactly vi, almost sure for every I belongs to n plus 1. So the theory describes the asymptotic behavior of the particle system through the cloud partition theta, which is characterized via the solution nu of the general traffic equation. It is not in principle a difficult task for a computer to solve the traffic equation by Massey, but we can present an algorithm of obtaining theta via a sequence of elementary comparisons using only the formula for the speeds v. Roughly, the algorithm goes as follows. So now I'll explain it in a more simple way. So start with, we have n particles. Then I look which particle has speed bigger than speed of particle which has number one more. For example, particle 5, which has b5 minus ay speed, bigger than b6 minus a6. In this case, for sure, our particle 5 in some time will reach particle 6, and they will be close to each other all the time. Now, close, it means that we will have some exponential estimations for distance between probability of distance between them. Then, now I can claim that this will be some subcloud. Forget about all other particles. So I have particle 5 and particle 6, and they have a5 b5 and a6 b6. Now I can find speed of this subcloud if it will be independent of all others. And now I have, and I'll close, this will be big particle. I called it big particle together. And I know speed. Now I have n minus 1 particles, one is big, and so on. And I look, is it possible to find two neighbor particles which have such speed that which is to the left has speed bigger than this? If such, they for sure will be in one subcloud. If this is subcloud, if I know this, using Jackson system and what we will do, I can find a new speed of this subcloud. And this I can do up to the moment that I have partition of my particles such that speed of any subcloud is, that will be that v1 will be less or equal v2, less or equal v3, and so on. And then they will go not interacted to each other. So this algorithm is reasonable And it's possible to find with our formulas because we got them already. So what I did with finger, unfortunately, I don't have blackboard, but what I did, I explain in a simple way what is written in this page. And this is more formal understanding how we can find all this speed. So algorithm, how to get to the answer. So my goal was only to explain the problem is solvable, why it is solvable, and for sure it is possible to write in a normal, rigorous language. But at the end, it is like, at the end, we will get partition of all particles.
Hello.
Yes. Somebody wants to ask? I don't know. Okay. So what
I have a question, Misha. I have a question. What will happen in case all A's and B's are, say, 1?
If all A, in this case, we will have, I want to speak. If all of them equal 1, then in this case, they will go, the speed of all of them will be 0. All of them will be 0. And in the situation, and distance between will, in this case, if you will find rows, they will be not less than 1. Rows will be equal 1. So they will be not distance between them. So in this case, for example, if you have 3 particles with rate like this, in this case, we will have nu1 and nu2, and or this row will be, and in this case, we don't have ergodicity, unfortunately. So if,
there will be no clouds there. So how many clouds were in that case will be? So just a single cloud, or you cannot.
No, we must. It will be single clouds.
Single cloud.
Single clouds. Because if you have single cloud, so all news will be not. So it's specific cases, and it's possible. What will be important that if, for example, nu equal, in the case when we have 3 particles, then anyway the system will be recurrent. It will be correspond to the case, not ergodic, but it will be recurrent. So with probability 1, all 3 particles will be close to each other. But if n will be equal, if we will have 4 particles, then it will be transient. It will be correspond to the model like simple random walk in 3 dimensions, like this.
Thank you, Misha.
Okay. Okay. Now I want to consider examples. Maybe it will be also some answers what you wanted to ask me before. So the partition example consists only of singletons if and only if bi, so speed of first less or equal speed of 2 less or equal speed of the last one. For example, what you asked me a minute ago, it was the case when this equal 1, this equal 1, this equal 1. and the above, if the above holds, then BI minus AI will be our speed of ice particle. All of them will go with the same speed. The intuition here is that particle I in free space has intrinsic speed BI minus Y, and if the speeds are not decreasing with respect to the order of the particles, the particle will meet very unfrequently, and so barely interact. So this is in some sense answer for previous question. Okay, the partition has a single part if and only if Vi with more or equal than Vn plus 1. So these numbers were possible to calculate for all I, where for all I belongs n, Vm, this is precise formula for which I must use calculator to find these numbers. So if all these Vi's more than this, then in this case it will be a cloud, and this cloud will goes with such speed. So all particles will go with the same speed. The intuition here is that Vi's is putative intrinsic speed associated with the subsystem of particles 1 to I, compared to the speed of Vn plus 1 with tilde of the whole system. A compact but less explicit expression of the stability condition is that lambda times 1 minus p to power less than 1, understood, also possible to understand, and this is the classical Jackson network stability condition translated to our model. So Jackson network, it was investigated in very deep way with many people of different levels who are really applied people and more theoretical. So I also want to say that maybe 30 years ago, why we were possible, first of all, why we were possible to study this problem, because many years ago, together with Guy Fayol, Sasha Sidorenko, and Vadim MALYSHEV and me, we tried to understand why Mr. Jackson was successful in his model. And we did it, we understood it using Lyapunov function ideology, and we found, yes, it was possible because we were possible to construct, in some sense, Lyapunov function. Jackson not use any Lyapunov functions, he precisely guessed what will be solution of his system and prove everything. But it was our understanding why it was possible to solve. So if you have clouds, so if all rows are less than 1, in this case, you can find all these V's, and you will see that this will be speed of our cloud. Also, suppose that all rows are less than 1, so all loads are less than 1, then there exists sigma square, which belongs to 0 infinite, such that if Z is normal distributed random variable, then as t tends to infinity, we have center limit theorem. So speed, position xi of t minus speed times t over square of t will converge to this. In distribution, we will be converged to this vector of random variables with 0 sigma square. What is the problem? That we can prove that sigma square exists, but really we can't find, for general case, we can't find this sigma square. But in the situation when we have n = 1, so we have 2 particles, we can find speed precisely, and we can find sigma square. So if we have only two particles, then if speed of left particle is bigger than speed of second, they will organize this. They will organize a cloud, a cloud, for which we can find speed, and we know law of large numbers, and we know central limit theorem. So, extremely nice problem for coursework, курсовая работа, for student of third year, try to understand why it happened, what to do, and so on. So if you have two particles with exclusion system, we can find precisely how their dynamics for a long time. Example, homogeneous drift. So if all this, if all bi's minus i's belongs to U, equal U, and I for all i's, then speed will be, all particles will go with this speed. Okay, so what I have, I must, okay. So this is precisely question which I was asked before. If bi's all no. If this is interesting example, if ai small between 0 and 1, and all others bi's are equal 1. In this case, we will call left particle dog, the dog, and all other will be sheep. So if dog not present, we will have sheep, and they will go with 0 speed. They will go with 0 speed together, and what was the question? What will happen? And speed will be 0. But we add some dog which want to move all sheep to the right. But if the number of sheep is big and dog is only small, we want to investigate what happened. What is interesting is that we can find lots for our case, for all of them, and all of them will be less than 1. What it means? That and at the end, all our animals will go to the right with slow speed, and we can find distribution for joint distance between all of them, and we can find expectation of distance between last right sheep and dog, and this distance will be about n times log of n. So if n is big, so distance between them will be bigger than constant times n. So here was when Vadim Alexandrovich first, it was this problem we started to do because of his interest. He asked me, what will happen in this case? And he used this many sheep and 2 dogs from the left and from the right. And his intuition was correct. He said that at the end, he predict that the distance between these dogs will be, he didn't use this word dog, it is my big improvement. I use dog and sheep. Well, that he thought that it will be n times constant. But I said, no, if I thought that it will be n times log n. So as very often in our life, both of us were correct in some sense. Because if you have only one dog and many sheep, then distance will be n log n. But if we have two dogs, then in this case, we also can find speed with which they will go. We can, rho k will be like this. So this problem is also solvable. And the expectation of this will be, I don't see here, but you can find in our paper that in this case it is strange. The distance between two dogs will be n times constant, and this constant we can find precisely. Okay, so I already told you, no, when I thought about this problem, I decided like first formulate and then explain what is the connection between our system, our particle system and Jackson networks. So I already explained that I precisely can find Jackson network for which input lambdas will be not zero only for first and last Q, and all we can find service rates will be find through AIs and BIs, and this also, and at the end we can find everything. So this is exactly our Jackson network. So here our lambda 1 will be, and for our case, lambda 1 will be A1, lambda n will be Bn, all this will be 0, all this will be 0, and these probabilities we also, and mu's we can find through AIs and BIs. I have to finish. Oh, but I had only half an hour. How I was going to give a talk?
No, we said that you have an hour. I told you that.
Yes, but I was thinking I prepare my slides for half an hour.
Oh, okay.
and I occupied all
But you
hour.
already,
Okay, good.
but you already present your talk in 55 minutes.
Yes, I must finish it because maybe so. Final remarks. No, in reality. So I want to tell you that now there are about this area, there are many interesting problems which are possible also to do. For example, if we have infinitely many particles, but all particles are starting from 0, for example, till plus infinite and near neighbors, and all have AIs, BIs. This problem, if, for example, all AIs equal to some number A and all BIs are equal to B, this problem when I gave a talk about Lomonosov functions, then Thomas Liggett came to me after my talk in Cambridge and said, and can you show what will happen using Lomonosov functions, that what will happen with our system? Fortunately, next morning, I showed him how to prove, to get the results which he knew from different way. And this was him. And here, and now this problem can be investigated when all AIs and BIs are different, and we can find formulas when the system will be in some sense stable. Also, it's a good idea to study when all AIs and BIs will be IID, random environment, and here also the answer will be like in Sinai regime in random environment. We also must study such things. So now it's in consideration, and maybe in a few months we will finish some paper with Andrew Wade and Sergei Popov. And maybe so many. And also this connected with results of many results of Pablo Ferrari, Luis Renato Fontes, but usually they considered not such problems. They want to study when we have infinitely many, and they are interested only in special measures. So they consider different technique. Problems which we want to consider usually more connected with when we can interpret it like Markov chain. And because my intuition is working only really in this situation. Maybe better than Pablo Ferrari is my good friend, and we wrote even joint papers, and I know where we are different. And really, when we are speaking, we can find some general language, but we are a little bit different mathematicians, and this is very nice. Okay, thank you very much.
Thank you. We can give an applaud to Mikhail if it is here. We have just 1 minute for question if we want to be strict with the program, but we will have ample of time in our breaks to discuss further. Questions?
Sorry, Misha, you have told in the beginning that the system consists of clouds, and each cloud has asymptotical velocity, but how it is possible that the size of the system increase like n log n if the asymptotical velocity is impossible?
No, n is fixed.
Yes.
And it's number of the
Right.
particles.
N is fixed.
And logarithm n is the size of the system.
Oh, on time. I see.
So
Sorry.
if you have many sheep
Yes, not on time.
and one dog, then I want to understand what will be the size of our system. And the expectation will be n times log n.
Oh, yes, not time. I see. Yes. And
And
what
if
is
you have-
what? Yes.
What will be the answer? But if you have two dogs from the left and to the right, and it will be like, and they will push, then the size will be n times constant. So some phenomena.
Thank
No,
you.
I have no time, and even
And
if
what
it will be discussion, I can
what was
explain
your
maybe.
answer to the question by Senya Schlossman? If all A's and B's are equals to 1, for example.
You know,
Yes.
I'm very sorry to interfere. What I suggest, if I may suggest, that we continue with the program, and then in the break, we still stay all together and we discuss. Is it okay?
Yeah.
Because
No, but-
I don't know, other
yes.
speakers, they probably ready to speak now. I'm
Yeah.
sorry. Let's go with
No,
the.
my
yeah.
little bit
better, I
talk because
think,
I
to
understand
have
that I not
immediately
reply.
answers.
Mhm. If Mikhail, do you want immediately answer?
No. Okay, maybe tomorrow I'll come if Sadovich will decide that university can look. I can come to university tomorrow.
But if you can shortly answer, there were.
What was the question?
All A and B's are equals to 1, for example. What is the size of the system? All A's and B's are 1. No dogs, only sheep.
Here expectation will be infinite.
Infinite for all time?
No,
Oh.
because if you have only two particles with the same speed, for example, 0, the
Yes.
distance between them, it will be not ergodic, not ergodic.
Yes, but for fixed time. Not ergodic. Oh, yes, of course.
Not ergodic.
Not ergodic. So there is, but there is no linear behavior. No clouds. Well, they collide. So there is no linear, no asymptotic.
No, because yes, in this case, No, they will go with speed will be, no, if like this, speed will be 0.
Zero speed, zero speed.
The,
I'm
yes.
sorry, then if it goes to long discussion, I suggest we do it in a
Okay.
break.
Yes.
Thank you. Thank you, Mikhail. We thank you once again. You can give upload over Zoom.